Okay, last video for the week here. Just kind of get you all wound down. We went through wavelength, near field, beam spread. That was pretty easy stuff. Now the last one here, just to kind of give you a little picture, we're dealing with Snell's Law. Okay? And that's going to tell us here, if we have one kind of material, whatever it may be, for this instance we're just going to say this is steel and this is plexiglass, what angle is that sound beam coming out of the transducer at? Okay? So nothing real terribly difficult, just trying to make sure we can figure all that out and see everything here, because we want to see these defects and we want to be able to see them as close as we can and as accurately as we can on these screens. Okay, and next week we'll start getting into screens and what they actually look like. So, here's our picture, here's our chunk of steel, never mind the fact that it's not level. We've got a shear wave coming out here. Let's just for fun say that it's going to be either 45, 60, or 70, oops, let me rewrite that, 70 degrees, okay? And that's going to be measured kind of in a plane like this. We're going to say that 45, 60, or 70 is coming from there over. Okay? So we need to know the calculation that actually makes that happen. That would be this one. Snell's Law. And Snell's Law tells us that if we have an angle and we take the sine of that angle, okay, more than likely it's going to be this angle right here. We'll call that angle 1, we'll call this angle 2. We're going to say if we have the sine of the measurement in this angle, and we have the sine of the measurement of that angle, we can take these two velocities and we can calculate any one of these defects just by cross multiplication. That's really all it is. So that tells us this. If we have a signal coming from here, and then it's going to bend and come down here, okay, this is the process of refraction, but basically that sound wave is going to come here at this angle, it's going to bend, and it's going to come out at this angle. And that always happens. If you have two materials with very dissimilar velocities, that's what's going to happen. So, let's just for kicks and grins plug some numbers in here and see what we come up with. Let's say our first material here is plexiglass. Okay, so I'm just going to plug in the velocity of plexiglass. About 110,000 inches per second. Okay, and I'm going to plug in two velocities. I'm going to plug in first the longitudinal velocity of steel and the shear wave velocity of steel. Okay, now don't get this confused. I'm actually writing two different problems here, but I'm just condensing space basically. And we have an incident sine or an incident wave coming in at about 40 degrees, let's just say. And then we want to know what the shear wave or the resultant wave is going to be in the steel. So that tells us this. We're in the plexiglass. This angle here, for fun, is about 40 degrees. What is our resultant angle right there? So here's our plexiglass velocity. Here's our angle coming up. Here's our steel velocity, longitudinal mode, because Snell's Law tells us that if we have two materials coming in like this, then we can have both a longitudinal and a shear wave all at the same time until we get past the first critical angle. Okay? So, let's just run this guy out. We need to do cross multiplication for both of these. So sine of 40 degrees, sine, on your calculator, 40. Make sure you're in degrees. I come up with about 0.642. Now I'm going to multiply that by 230,000. Whoa, pushed the wrong button there. Sine of 40 degrees times 230,000 equals 147,841. Okay? Now, we've done this times this. We need to divide by this. So we divide by 110,000 That gives us a value of 1.34, which in turn, if we do shift sign or inverse sign of that, that tells us that we have an error. If you have anything greater than 1, when you get to the sign, whoops, this means that you've passed either the first or second critical angle. So that means this. Incident wave comes in. Here is, again, longitudinal wave coming up. We keep bending this thing down far enough. We're going to actually have a longitudinal wave that's either scooting along the surface or has been completely bounced out, leaving us with just a shear wave. Okay? So in this case, that's what's happening. And that's not a bad thing. So that just tells us this. Let's go back here. This times this divided by that. Sine of 40. 0.642 times, instead of 230,000, we're going to say 130,000 this time. That's 83,562. So that's much better. And that was actually wrong. I wrote that wrong. 83,562, and that's going to be divided by 110,000 and not 1.34 like I had it wrote before. So divide that by 110,000, and I come up with 0.759 now. Less than 1, we know it's going to be an angle. Inverse sine, I've got 49.43 degrees. Alright, so that tells us this. We're past the first critical angle, so let's get rid of that. Longitudinal wave's gone. At 40 degrees here, we have a resultant shear wave at 49 degrees. Okay? A little bit past 45, in between 45 and 60. Nothing wrong with that. Okay? Just tells us with a relationship here, we get a relationship here. As long as you can plug these numbers in right here and run them through, cross multiplication, then you're in good shape. Now, the other way is just working it backwards. Okay, if you start out here, if you're given a number here and not here, just work it backwards. This times this divided by that equals that. Okay? Just cross multiplication. And again, if you have any issues, please let me know, email me, whatever, and we will work them out. But I'm going to let that soak in for just a second here. And then if I need to put on more videos or anything like that, I can do that as well.